Welcome back to MiniTorch. Today we'll cover Module 2.3, Advanced Tensors. This is a relatively short lecture and is supplemented by the Tensor Puzzles. There will be another video with explanations of how they work, and you can check them out on GitHub. Before we get there, though, let's review some of what we learned last time. We introduced higher-order functions that allow us to transform our tensors. The first of these was relatively simple. This was map, where each index of the first tensor gets mapped to the same index of the new tensor. Next, we saw zip, where indices were paired between two tensors to produce a new value. Finally, we talked about reduce, where a single dimension of the tensor is reduced to size 1. This produces a new tensor that has that dimension of size 1 and all the other dimensions of the same size. In this example, we go from 3 by 2 to 1 by 2. In today's class, we'll review a bit more about broadcasting, and we'll talk about the future use of gradients and introduce the tensor puzzles. So let's review how broadcasting works. The motivating challenge of broadcasting is that we want to extend the zip operation to work not just on tensors of the same shape. For example, if we want to add a scalar value to a vector, we'd like to automatically and implicitly increase the size of the scalar to the size of the vector so that we can add them together. We'd like to do this without running a for loop in Python and without using any additional memory. A more complex and common example is when we want to zip together two matrices that have different shapes. In this example here, we have one matrix that's 3 by 1 and one that's 1 by 2. We would like to zip these together to a 3 by 2 matrix. It's relatively straightforward once we have all the shapes to figure out where values come from. For example, index 1, 1 in the final output probably comes from the second row of the first input and the second column of the second input. That corresponds to basically picking the dimensions that exist and using dimension index 0 for the other dimensions. In order to figure out these shapes, though, we need to determine a protocol. This protocol is known as broadcasting and has the following rules. The first rule is that the dimension of size 1 broadcasts with anything. The second is that we can explicitly add a dimension of size 1 whenever we want using the view method. And finally, zip will automatically implicitly add an extra dimension of shape 1 to the left if it needs to. Last class, we played through various different examples to determine the final output shape. The general rule that I would recommend is to right align the two shapes like this. If we have one tensor of shape 3, 4, 1 and one of 1, 5, we can align them to the right and see that they produce a shape of 3 by 4 by 5. You can go through a couple examples to convince yourself that this works. And in this example here, we're applying both Rule 1 as well as Rule 3 in order to make this work out correctly. Rule 2 tells us that we're allowed to explicitly add an extra dimension if we want with view. View is relatively straightforward. You give it the new shape, and if that shape is valid, it will work. Otherwise, it will fail. So here I have a tensor of shape 3, which I can view either as 3 by 1 or 1 by 3. Each of these will produce a new shape, and while this doesn't actually change the underlying data, it can make broadcasting work. You're in some sense telling Torch to interpret it as a row or a column vector. Now let's look at some more examples of broadcasting. Here's an example where we start with a shape that is 3 by 2, and we add it to a shape that's 3 by 1. These two broadcast together, so they produce a matrix that's 3 by 2. This is a relatively straightforward use of broadcasting, but I write it here so we can look at what's happening behind the scenes. Here's what this looks like in terms of pictures. The first value is 3 by 2. The second is 3 by 1. We can think of the second value as expanding to the right. One way of thinking about that is making two copies of the original data. Those copies don't actually get stored in memory, but you can think of them as being implicitly created. We then zip together these two shapes, which are of the same shape, and we produce our final output tensor. Here's another example. Here I'm using a method called zeros, which produces a tensor of a given shape. The shape of x is 4 by 5, and the shape of y is 3 by 1 by 5. Zipping these together produces a 3 by 4 by 5 tensor. We can look what this looks like in terms of pictures. The first is a 1 by 4 by 5 tensor. The second is 3 by 1 by 5. Remember, it's depth, row, columns. When we zip them together, we are making 3 copies of the first tensor, as shown by the yellow line, and making 4 copies of the second tensor. Remember, these don't actually get created in memory. Writing this down in MiniTorch code, this is like creating a 3 by 2 matrix as well as a 2 by 1 by 2 tensor. We can then broadcast these together through multiplication. This gives us a 3 by 2 by 2 tensor. We then sum out the final dimension, producing something that's 2 by 3 by 1. We can reshape this again to a 2 by 3 matrix. Looking at the full process, here are the 2 tensors we created on the previous slide, the 3 by 2 matrix and the 2 by 1 by 2 tensor. When we do the multiplication, this is like expanding both of these out. The orange parts show the imagined repeats that happen in the broadcast. Again, noting that this doesn't actually get created in memory. We can then multiply these two element-wise together. We then do a reduction along one of the axes. The axis where the reduction happens is along the columns. So this goes from 2 by 3 by 2 back down to 2 by 3 by 1. We can then reshape this to a 3 by 2 matrix by using view. Finally, let me last talk a little bit about the implementation of this in MiniTorch as well as in PyTorch. The key idea, as I've repeated several times, is to never create an intermediate value. If we did this, we'd have to pay an exorbitant memory cost, and it would often not actually help us in practice. The other thing to remember is that you are trying to create some output tensor, which you know the size of, and so you can work backwards and figure out where it came from. In the code, there will be 2 functions you'll work with. One is called shapeBroadcast, which will create the final output shape, and another that is called broadcastIndex that will figure out this reverse process. Using these primitives, we'll have 3 low-level operations, which will be implemented as higher-order functions. These are the same 3 higher-order functions we saw from Module 0, map, zip, and reduce. We'll implement these several different times. First, in a simple implementation, which we'll use for debugging, then a CPU implementation, and finally a GPU implementation. This is going to be the focus of the lectures in Module 3. These functions have the following type signature. Map takes in a mathematical function from float to float and turns it into a function from tensor to tensor. Zip takes in a function from 2 floats to a float and returns a function from 2 tensors to a tensor. Finally, reduce takes in a function that maps from 2 floats to a float, as well as a starting floating point value, and then produces a function that maps from a tensor and a dimension to a tensor with that dimension reduced. In order to actually apply this to different functions in practice, we introduce a way to take any of the operators that you introduced in Module 0 and turn it into a higher order operator. So for instance, a neg map here applies negation to every element in a tensor, producing a new tensor. Here's how to use it in practice. If you're implementing this on the lower level, you can take in a tensor and apply a neg map. Now, just to be clear, this is not how users will actually use these operations, but you might find this useful when implementing it in practice. Finally, the last thing I want to note today is that for the lectures coming up, we have a series of additional videos that take the form as interactive puzzles. When I teach this in class, we often do these puzzles in class and work through them together. To simulate that experience online, I've made additional videos for each of the puzzles. If you search for my name and Tensor Puzzles, you'll be able to find a walkthrough of these puzzles. I do recommend doing these first on your own, though, before looking at the answers. To provide some additional background to help you out with these puzzles, I want to note some of the special syntax in PyTorch that we don't have implemented in MiniTorch. In particular, one syntax I find very useful is using the none keyword in Python to add a dimension of size 1. So for example, you'll often find it very useful to add in these extra dimensions. If we want to transform a tensor that's shape 3 to one that's 1 by 3, we can simply use none to add in that extra 1 dimension. You can either do it like x none, which will add the dimension first, or you can use the colon syntax to indicate that none should be added after the first dimension here. Another function that you'll find very useful is the arange function. If you call arange with an integer value, it will create a tensor that counts from 0 to 1 minus that value. So this looks like a tensor equivalent of the torch range function, and it is a nice way of producing tensors that correspond to the values from 0 to a given position. Another useful helper function in tensor languages is torch.where. Torch.where acts like an if statement, but applied to every dimension of a tensor simultaneously. So if I pass in as for my first value, a tensor of values true and false, this will return values from the second and third tensor that correspond to true or false. So if the value is true, then it pulls the cell from the first tensor. If the value is false, it pulls the cell from the second tensor. So in this example here, passing in true, comma, false produces a tensor that's 1, 0, i.e. the value from the first tensor and then the value from the second tensor. This can get more complex, so check out the tensor puzzles to see how they work in practice. Okay, that about does it for this lecture today. Next class, we'll move on to cover gradients, which will be the last part of our Module 2. See you then.